So in this screencast we're going to look at a carry lookahead adder. So we've seen in a ripple carry adder, the carry out of each stage is a function of the carry out of the previous stage plus the inputs to that stage. So the fact that the carry out of each stage depends on the previous carry out of the carry out of the previous stage is the root cause of the slow speed of a ripple carry adder. So there's a different type of adder called a carry lookahead adder, or CLA. Now this is designed in such a way that the carries of each stage, so CI, are purely a function of all the input bits, so all the A and B bits, and the very first input carry to the adder. So because the A's and B's and the first input carry are all known at time 0, it means we can actually calculate the carries for all the later stages at the start without waiting as we kind of ripple along this chain. So this means that the carry lookahead is essentially a fast adder. It's got much better performance than the ripple carry adder. So we'll consider the cases now of actually how we create a carry out. So for a full adder, there's two ways. In fact, we create a carry out. The first way is when A and B are both 1. So we know in the case when we do the Boolean arithmetic, 1 and 1 gives you 0, carry 1. So we say in that case it generates a carry. So we do 1 plus 1 will generate a carry. And another way with a full adder we can get a carry out is essentially if there's an input carry to the full adder, and then that just passes through the full adder to become the carry out. So we call this propagating a carry. So we've got our full adder, we've got a C in and a C out. So if we get an input carry and that just passes onto the output carry, we'll say we're just propagating it, we're just passing through this carry. So those are the two ways we can generate a carry. So we can see these actually from the truth table. So this is for the top half of the truth table. When there's no input carries, we actually generate an output carry here when A and B are both 1. And then for the second half of the truth table, when we've got input carries, we'll see we get an output carry for these 3 cases here. So you can see this is the first 2 are propagating the carry, and then this last case here we can also say that's generating, because that's the same case here, adding up A and B are both 1. So that can be classed as generating a carry as well. So from that truth table we can obtain expressions for the carry generate and carry propagate. So we say carry generate is A and B. So from this truth table we can just see when we've got A and B we create a carry, so we call this the generate. And then we also, if we look closely, we can see that we propagate a carry. So we're saying that these 2 are the generate, and we can say that we're going to propagate. For that case, we can see A and B are different, so an XOR function. So the carry generate is just A and B, and the carry propagate is A XOR B. So you can see in this case we chose to use a XOR function, but we could also, the fact that we've got 3 here, we could have used an OR function to do that, but we'll actually use A XOR B, because we see that order A XOR B already appears in the full adder circuit, so it means we can reuse that XOR gate. So that's the reason we choose to use the XOR. So we'll look at the circuit for a full adder now, and essentially we can add in a separate 2 separate outputs. So this output here, the output of this gate, we can call a propagate output. So again, that's why we chose to use this XOR. We've already got the XOR gate here in the full adder, so we can just reuse that gate to call create the propagate. And then again the generate is A and B. So we'll just take this output here to be the generate and this output here to be the propagate. So you can see this this is what the full adder circuit essentially does. So we've actually got, there's two ways of creating the carry out, propagate or generate it. So that the actual carry we get is that we can either generate, a carry from A and B, or if we're propagating and we get an input carry, we'll create a carry. So you can see this is, this circuit just enforces the behaviour of the propagate and generate. So now we've got these new terms for propagate and generate, we can rewrite the expressions for the sum. So this is a normal expression we've seen for the sum before, and that we now know that we're calling A XOR B the propagate function, so we can just rewrite that and say the sum is given by this propagate XOR the carry in. And again, this is a expression we've seen before for the final carry out. And we know now that's our generate function A and B, and then that as our propagate function, so we can just rewrite the expression for the carry out in terms of the generate and the propagate and the input carry. So again, it's just reinforcing that same, it's just a different way of saying the same thing. So we basically get a final carry out if we generate a carry. So we can either generate a carry, or we've got an input carry and we propagate that carry through the full adder. So the next step, we can just write the carry out expressions for each stage in the full adder, in the adder, in terms of the carry, propagate and generate of that stage. So this is just the case when we got for a 4-bit adder, for example. We've got our 4 full adders. So we can say carry 1. So carry 1 is the output. This is stage 0, 1, 2 and so on. So we've got C0 is this input carry, C1 goes into here, C2 and so on. So we say we've got C1 is just equal to G0 or P0 and C0, and we can just do that for each subsequent stage. So we've got these 4 expressions now. So you can see this is still not ideal, because see the carry out of stage of C4 still depends on C3, and then C3 depends on C2, C2 depends on C1, C1 depends on C0. So this is still showing this kind of, they're still suggesting that the carry depends on the previous stage. But what we can actually do, we can just substitute in the early expression. So we know C1 is given by this. So for the expression for C2, we can just stick this expression in here and then multiply it out. And again, we can stick C2 into here, this expression into here, and just multiply out those expressions to be left with these 4 expressions now. So this is obviously much more complicated logic, there's more terms involved and so on, but the good thing now is we can see, so if we take the last carry out, so C4 for example, we can see for this expression it only depends on C0. So this is known at time 0, and all the propagate, remember all the propagate and generate bits, they all just depend on A and B. So all of these come from A and B, which are also known at time 0. So essentially we can see the carry outs of all the stages depend only on the propagate and generate bits and this first carry in. So then if we apply the inputs A and B and the first carry in, we say that they're applied at time 0. Because the propagate and generate bits, they're just an XOR gate and an AND gate, we're going to know all of the generate and propagate bits for all stages at T1. So this is for stage 4 and stage 1, all the stages we know the propagate and generate bits at time 1. Now we've got these expressions here, but we can see these are just similar to SOP expressions. So for this case it's just a 5 input OR gate, and each one of these is essentially an AND gate, so that this is a 5 input AND gate, we'll have an AND gate for this one and so on. So we can see there's actually just two, to generate this carry is just 2 gate delays. So 1 gate delay here, 1 gate delay here. So there's 2 levels of gates there. So if we generate the propagate, if we know the propagate and generator bits at time 1, we actually know all the carry bits at time 3. And then we know from the full adder circuit the sum bit just has to go through this final XOR gate. So we know the sum at time 4. So we know all the carry bits at time 3 and the sum at time 4. So we can see we've actually half the time compared to a ripple carry adder, because we saw with a ripple carry adder it takes 8 gate delays to calculate the 4-bit sum. But with a carry lookahead adder, we can actually do that in 4 gate delays, and it's this is true also for when we get there's actually much bigger savings compared to ripple carry adders as we increase the number of bits in the adder. So we'll look at a 4-bit carry lookahead adder now. So we've got our 4 full adders, but now we've just added in these propagate and generate terms. So from that circuit we can just tap off the propagate and generate signals. So we assume at time 0 we stick all the inputs in and these the first carry in, so we get all those at time 0. So it means that, so essentially at time 1 we'll have P and G, we'll calculate those at P after 1 gate delay, and we can put that, so all the big expressions we saw for the different carry bits, you normally see that drawn as a separate circuit, the lookahead carry generator, but that inside there is essentially just the logic to implement these. So these are just normally shown in this separate circuit. So after a couple of delays in there, we'll have all the carries. These can then get fed into all the full adders in the circuit, and then we'll generate our sums. So you can see it's much quicker. So we're not, C in here is not coming from C out of the previous stage like it was before. We're getting the carries from this lookahead carry generator, which we essentially know after just a couple of gate delays at the beginning. So there are some limitations for the carry lookahead adder. So for the case of the 4-bit adder we've just seen, the final carry out C4 requires a 5 input OR gate along with 5, 4, 3 and 2, 1 input AND gate. So you can see that's the logic we need to implement this. So essentially we've got this sum of products type expression. So we've got 1, 2, 3, 4, 5. So we need a 5 input OR gate, then we need a 5 input AND gate, 4 input AND gate, 3 input, 2 input, and then we've just got this generate function on its own. So there's practical limitations to this. So if we follow the logic through for an 8-bit carry lookahead adder, for example, we'd see that we need a 9 input gate, and then for a 32-bit adder we'd require 32 input gates. Now it's just not practically feasible to manufacture logic gates with so many inputs, and so the approach for creating larger carry lookahead adders, we normally combine together 4-bit carry lookahead adders in a hierarchical manner. So if we wanted to create a 16-bit adder, we could implement that with 4-bit carry lookahead adders. Then we'd also need this additional level of the carry lookahead logic. But even for that case, a 16-bit carry lookahead adder can do the sum in only 8 gate delays as opposed to 32 using a 16-bit ripple carry adder. So there are still, the circuit's more complex. We've got all this combinational logic to implement the carry lookahead. It's still much faster. So it trades more complex logic in terms of much greater speed. So if we wanted to kind of create this 4-bit, we can put this 4-bit carry lookahead together into one package. So again, we've got our two 4-bit inputs now, A and B, our carry in, and our sum. But then we also add these two extra outputs. We've got our group propagate. So this group propagate output here, and that is just given by the AND of all the propagate bits from the individual bits inside, and that's just going to tell us if the 4-bit group will propagate any carry what comes through here. And then we've also got the group generate output, and that's just saying if this individual 4-bit block will generate a carry. So we can see, so we know the group itself will generate a carry if the 3rd bit generates a carry, or if the 2nd bit generates a carry which is then propagated through the 3rd bit, or if this 1st bit, so bit 1, generates a carry which then propagates through 2 and 3, and then, or we generate a carry in bit 0 which then propagates from 0 to 1 to 2 to 3 to the output. So these two extra outputs are just given by this additional logic, and that tells us whether that 4-bit group will generate its own carry, or whether it propagate any input carry through the group. So now this diagram here shows how we can create a 16-bit carry lookahead adder. So now we've got our four 4-bit adders, so we can just tap off. So bits 0 and 3 will stick into this group, 4 to 7 in here, 8 to 11, 9 to 15 for example. And then from these group propagate and group generate bits, we can use that to calculate this, and then from these ones calculate that, and so on. And again, each one, so this 4-bit adder here will output 0 to 3 bits of the sum, and bits 4 to 7 of the sum, 8 to 11 of the sum, and 9 to 15 of the sum. So from, and this is the same, should be noted, this is just the same logic as we used in the 4-bit carry lookahead adder. We just add another level of that. So we could just do the same again. If you wanted to create a 64-bit carry lookahead adder, you could, get 4 of these circuits all connected together with another lookahead carry generator. So that's how we tend to create. That's how we create these larger carry lookahead adders. Because if you think about, remember that the lookahead logic is essentially this SOP type expression, this and an OR term. So there's only 2 levels of gate. So for each additional lookahead carry generator we use, there's only a couple of extra gate delays implemented. So we get, as you increase the number of bits in the adder, it doesn't actually kind of double or quadruple the adders, the delays as it does with a ripple carry adder.